Hello and welcome back to the Topictrick channel. It is fantastic to have you here with us today. Whether you are a computer science student just starting out, a fresh graduate stepping into your first role, or an experienced database professional looking to sharpen your skills, you have come to the right place. Today, we are going to tackle a subject that is absolutely critical for enterprise data management. We're talking about DB2 Performance Tuning. Now, you might be asking, what exactly is DB2? Simply put, DB2 is IBM's enterprise-class relational database management system. It is the engine behind banks, insurance companies, and massive retailers around the world. But having a powerful engine is not enough. You have to tune it. Performance tuning is the art and science of making your database run faster, more efficiently, and more reliably. It's about ensuring that when a user asks for data, they get it immediately, without waiting. By the end of this session, you are going to understand the architecture behind DB2, the specific knobs and levers you can pull to improve speed, and how to troubleshoot real-world problems like a pro. So, let's get started. To tune DB2 effectively, you first need to understand how it works under the hood. You cannot fix a car engine if you don't know what the pistons and spark plugs do, right? The same logic applies here. At the highest level, you have the DB2 instance. Think of the instance as the environment or the container where your actual databases live. Inside that instance, you have the database itself. Within the database, memory is king. The most important memory structure you'll deal with is the buffer pool. This is a chunk of memory where DB2 caches data pages. When you run a query, DB2 looks in the buffer pool first. If the data is there, it's fast. If not, it has to go to the physical disk, which is much slower. Speaking of disk, we have tablespaces. These are logical storage units where your actual tables and indexes reside. Finally, there is the logger. Every time you make a change, an insert, an update, or a delete, DB2 writes that change to a log file first to ensure recoverability. When you submit a SQL query, it goes through a pipeline. It's parsed, optimized by the DB2 Optimizer, and then executed. Understanding this flow is essential because tuning usually involves fixing a bottleneck in one of these specific areas. Now, let's dive into the core of today's discussion, which is the key performance tuning areas. We're going to break this down into digestible pieces, starting with buffer pool tuning. As I mentioned a moment ago, the buffer pool is your first line of defense against slow performance. The golden rule here is simple. Accessing memory is thousands of times faster than accessing a hard drive or even an SSD. Your goal is to keep the buffer pool hit ratio high. This ratio represents the percentage of time DB2 finds the data it needs in memory rather than reading it from disk. Ideally, for a transaction processing system, you want this to be above 95%. To achieve this, you need to size your buffer pools correctly based on your available system RAM. You also need to consider page sizes. DB2 supports 4 kilobyte, 8 kilobyte, 16 kilobyte, and 32 kilobyte page sizes. Generally, if you have random access to small rows, smaller page sizes work well. If you're doing data warehousing with massive sequential scans, larger page sizes are often better. Next up is table space and storage optimization. How you lay out your data on the physical disk matters. In modern DB2 environments, you'll mostly use automatic storage. This allows DB2 to manage the container creation and extension for you. However, you still need to decide between a system-managed space, known as SMS, and database-managed space, known as DMS. For performance, DMS is almost always the superior choice because DB2 interacts directly with the disk, bypassing the operating system's file system overhead. You also want to look at your extent size, which is the number of pages written to a container before moving to the next one. Ensuring your extent size aligns with your storage array's stripe size can significantly reduce I/O wait times. Let's move on to one of the most impactful areas, which is index tuning. If your database is a library, an index is the card catalog. Without it, you have to walk down every aisle and check every book to find what you need. That's called a table scan, and it's usually bad for performance. There are two main types of indexes to understand. First, the clustered index. This actually organizes the physical data in the table to match the order of the index. You can only have one clustered index per table. Then you have non-clustered indexes, which are logical pointers to the data. The most important concept here is cardinality. Cardinality refers to how unique the values in a column are. A column like Social Security number has high cardinality because every value is unique. A column like gender has low cardinality. Indexes work best on columns with high cardinality. A common mistake is over-indexing. Every time you insert or update a row, DB2 has to update every single index on that table. If you have too many unused indexes, you're slowing down your writes significantly. You can use DB2's administrative views to identify indexes that have never been used and drop them. Now let's talk about the heart of today's discussion, which is the SQL query tuning. You can have the best hardware in the world, but a poorly written query will still bring your server to its knees. SQL tuning is about helping the DB2 Optimizer find the best path to the data. A classic anti-pattern is using select star. This pulls back every single column, consuming unnecessary I/O and memory. Always specify only the columns you need. Another area to watch is functions on columns. If you write a query where you apply a mathematical function to a column in your where clause, DB2 often can't use the index on that column. It has to scan every row to calculate the value. To tune SQL, you use the explain facility. Tools like DB2 EXFMT give you a visual representation of the access plan. You want to look for expensive operators like table scans on large tables or unnecessary sorting. You also want to check the join order. DB2 should ideally join the smallest set of data to the larger sets to minimize the intermediate memory usage. Speaking of memory, let's discuss memory configuration. DB2 memory is split into different heaps. You have the database memory, the sort heap for sorting data, and the lock list for managing record locks. Tuning these manually can be difficult because workloads change throughout the day. This is where STMM, or the Self-Tuning Memory Manager, comes in. STMM is a background process that constantly monitors memory demand. If your queries start doing a lot of sorting, STMM can steal a bit of memory from the buffer pool and give it to the sort heap. For most users, enabling STMM is a best practice. It simplifies administration and adapts to changing workloads dynamically. However, in very strict, stable environments where predictability is more important than flexibility, some advanced administrators prefer to set values manually. Moving on, we have concurrency and locking. Concurrency is the ability for multiple users to access the system at the same time. Locking is the mechanism that prevents them from overwriting each other's work. But locks cause waiting. You need to understand isolation levels. The default in DB2 is cursor stability. This ensures that a row is locked while a cursor is positioned on it. If you have a report that just reads data and doesn't need perfect accuracy, you might use uncommitted read. This allows the query to read data that is currently being changed but not yet committed. This is risky for data integrity, but great for performance. A major headache in this area is the deadlock. This happens when transaction A holds a resource that transaction B needs, and transaction B holds a resource that transaction A needs. They're stuck waiting for each other forever. DB2 will eventually kill one of them to break the deadlock. To reduce this, ensure your transactions access tables in the same order and keep transactions short. The last technical area we'll cover is logging and recovery. Every transaction is written to the transaction log buffer before going to disk. If this buffer is too small, your application waits for the flush to disk. Increasing the log buffer size is a quick win. Also, ensure your log files are on a separate physical disk from your data files. This separates the sequential write I/O of logs from the random read I/O of data. Now that we've covered the theory, how do you actually see what's going on? Let's talk about monitoring and diagnostic tools. There are a few tools every DB2 professional should know. First is DB2 PD. This is a command line tool that reads directly from the shared memory. It's incredibly fast and lightweight. It's perfect for troubleshooting a hung system because it doesn't require an SQL connection. Next is DB2 Top. This is a text-based interface that looks a bit like the Linux top command. It gives you a real-time dashboard of your buffer pools, locks, and sessions. It's great for spotting current issues at a glance. For historical analysis and deeper dives, we use the MON get table functions. These are SQL functions that let you query the database's internal metrics, just like a regular table. You can write SQL to find the top 10 queries consuming the most CPU time. So, let's put all this into practice with some real-world tuning scenarios. Scenario number 1, the suddenly slow query. A user complains that a report that used to take 5 seconds now takes 5 minutes. What do? First, check if the data volume has changed. Then, check the statistics. DB2 relies on statistics about the data to build query plans. If the table grew by 1,000,000 rows but the statistics haven't been updated, the optimizer might choose a bad plan. The fix is often running the run stats command to update those statistics. Scenario number 2, high CPU usage. You look at your server and the CPU is pegged at 100%. Use DB2 Top to identify the specific application causing the load. Often, high CPU is caused by sorting. If you see a lot of sorting, check your SQL. Can you add an index that is already sorted? Or check if you are doing a table scan on a massive table because of a missing index. Scenario number 3, locking bottlenecks. The system feels sluggish, but CPU and I/O are low. This usually points to locking. Use DBPD with the locks option to see who is holding locks and who is waiting. You might find an application that opened a transaction, updated a record, and then went to lunch without committing. The fix here is usually on the application side, committing transactions sooner. Finally, scenario number 4, poor buffer pool hit ratio. You check your metrics and see a hit ratio of 80%. This means your system is thrashing the disk. The immediate fix might be to increase the size of the buffer pool if you have RAM available. Alternatively, look for index scans versus table scans. A table scan floods the buffer pool with data that might not be needed again, pushing out useful hot data. Before we wrap up, I want to summarize some best practices and highlight common mistakes to avoid. One of the biggest mistakes is the set it and forget it mentality. Performance tuning is a cycle, not a one-time event. You must monitor continuously. Another mistake is ignoring statistics. I cannot stress this enough. Run stats is your friend. Automate your maintenance windows to ensure statistics are always up to date. Also, do not assume adding more memory will solve everything. If you have a bad query doing a Cartesian join, throwing more RAM at it won't help. You have to fix the root cause, which is the code. And finally, verify your storage layout. Ensure your transaction logs are isolated and your storage paths are spread across multiple physical disks or LUNs to maximize I/O throughput. To recap what we have learned today, we explored the DB2 architecture and the importance of memory and logging. We broke down the vital tuning areas, buffer pools for caching, indexes for fast retrieval, and SQL tuning for efficient execution. We discussed how to handle memory, concurrency, and the tools you need like DB2 PD and DB2 Top to diagnose issues. Remember, a well-tuned database is a silent database. It does its job quickly and efficiently without anyone complaining. I hope you found this session helpful and that you now feel more confident in tackling DB2 performance challenges. If you enjoyed this video, please give it a thumbs up and consider subscribing to Topictrick for more technical deep dives. We have plenty more content coming your way. Keep learning, keep tuning, and we will see you in the next video. Goodbye for now.